Okay, so I'll share my screen. Is my screen is visible? Is my screen is visible? Please respond. Is my screen is visible?
Yes, ma'am.
Okay, thank you.
Yes, ma'am.
Okay, thank you. No, ma'am. Please check your connection too. Okay, so 23, so we can, let's wait for 1 minute, 24 seconds. So earlier we have discussed, yesterday I was not able to take the class because I went for some test. Okay, anyways, so today I'm taking combined class, okay? So in the both the classes, section A and section B, we have discussed theories of failure, and we have discussed two more theories also. But I'll discuss all the 5 theories today also. Okay. So those who have issue, please let me know later on. So please, CR, if CR is in the group now, please put a message that class will start in soon. 30, perfect. Please give a message on the chat box, your personal chat box, a WhatsApp group that class will start soon. Okay, 33, 34. Okay, so let's do a quick review that we have studied about. This the theories of failure, right? We have studied that why we need. First, we have discussed that why we need theories of failure. As simple as that. Suppose if you have, this is my material, I need to if this material is getting stress from all the direction, this direction, this direction, and this direction. This is a complex state, right? To find the stresses in these complex states, we need theories of failure. If we need to find the stresses only in one direction, so we can use UTM, universal testing machine, and we can find the value of sigma y or sigma u. Remember the stress strain curve. This is the elastic limit, then it will go to yield portion, upper yield, then it will come to this. So this is your sigma u, ultimate strength, and this is the, let me note once again. So this was our stress strain curve, elastic limit, yield. This is the breaking point. This is our ultimate sigma u. This point will be, let me share once again. A blank PPT is visible.
Ma'am.
Okay. So as we discussed, this is our stress strain diagram. So this is the elastic limit, then it will have yield this, and this will be the breaking point. So this is the ultimate strength, which is also, I'm representing this, and this is our yield stress when your deformation will start. And this yield was for ductile material, and this the ultimate strength was for brittle material. Okay. Always remember, for brittle material, ultimate strength means the critical limiting stress. The value, all the stresses should not cross sigma u for brittle material, otherwise it will fail. And for ductile material, this is the limiting. After, if the stresses sigma 1, sigma 2, we got right principal stresses. If this principle, or if you take 3D, 3 dimensions, then there will be three stresses. So if these values increase, if these values should be less than this sigma y for ductile material, then your structure will be safe. But for brittle materials, these values should be less than sigma u, then your structure will be safe. So our first theory was principal stress theory. Okay, what principal stress theory says that? It says that your maximum principal stress, that is sigma 1 or sigma 2. Okay, you can take sigma 1 or sigma 2. So this principal stress should be less than or equal to your sigma. I'm taking just first, I'm taking sigma y. Okay, just I'm considering that your principal stress should be less than or equal to its limiting strength. Okay, so if this is the condition for no failure condition. No failure, no failure. This is for no failure condition. If this value becomes more than the sigma y, then your structure will fail. Okay, so now I'm taking tension as positive and compression as negative. So suppose this is my component, this is my stresses. Okay, so suppose sigma 1 is in tension, which is positive. It can be also in compression. In this theory, it is assumed that if you are applying tension of 50 Newton, it will give you back the 50 Newton tension. All the material properties, all the phases in this component will act only 50 Newton. And if I am applying 50 Newton compression, then all the materials will experience 50 Newton of compression itself. Okay, so so you can have this one condition. If I am applying tension, sigma 1 should be less than and equal to sigma y. Then there will be another condition. Let me remove this part. So if this could be the condition, right? Again, I can do if I'm taking the another portion, another plane. So I have sigma 2. This can be less than sigma y, right? And I can take compression sigma 2 also. It should be less than y. So these four are the equations of this theory, which are the conditions for no failure. So if any one of this value, that the maximum principal stress, if increases your limiting yield strength, then your structure will fail according to this theory. And if I want to represent this theory in coordinate form, if I want to represent this equation in coordinate form, so suppose this is my sigma 1, this is my minus sigma 1. This is plus sigma 2 and this is minus sigma 2. So you must have gone linear equations in your mathematics. So if I want to plot the curve for these equations, so I'll get a perfect square. Suppose this is my, for this equation, suppose this is my, let me draw with another color. Suppose for this equation I have sigma 1 here. Okay, this minus sigma 1, this point is here, plus sigma 2 is here, and minus sigma 2 is here. So if I join this point, I'll get a perfect square. Okay, so the value of sigma 1 and sigma 2 should be, this is the region, this is called safe region. Safe region. Okay, safe region. If your values come inside this value, suppose you are getting value here, so your structure will be safe. If you are getting sigma 1 and sigma 2 here, your structure will be safe. If your value lies at this point or at this point, so your structure will be unsafe. Okay, the stress generated on that will be unsafe for that structure as per this theory. So for this theory, your shape of the safe region is in shape of square. Okay, and these are the conditions of these are the four conditions for this as per this theory. If this are in this limit, then this is the no failure criteria. Your structure will not fail. So in simple language, that as per this theory is that your maximum principal stress, either sigma 1 or sigma 2, should be less than your sigma limiting. It should be less than for your limiting strength it should be less than your limiting strength. Now, as this theory is applicable to only brittle material, Okay, is this theory is only applicable to brittle material. So for brittle material, what is the limiting strength? It is sigma u. So you can write sigma u here. Okay. So as per this theory, your sigma 1, the maximum value should be less than your limiting strength, which is sigma u in these cases. I have taken an example. I have just shown you an example by sigma y, but for this theory only works for brittle material. Okay, and brittle material, what is the critical strength or limiting strength? It is sigma u. Understood this theory? Shall I move to the next one? Please response. I have to be bit fast, so let me know. This theory is clear. Shape of the safe region will be square. These are the four equations. It is applicable for brittle material. Okay, let me show the PDF. Yes, Likha, why you have raised hand?
Sorry, ma'am. Sorry.
No issue. I thought ki you must have any confusion. Is it so?
No, ma'am.
No. Okay. So let me show the theory part in the PDF file. Just give me a minute. So this is my PDF is visible, I guess, right? So Rankine state maximum principal stress theory as follows: a material fails by fracturing when the largest principal stress, either sigma 1 in 2D and sigma 3, or you can take, let me admit some. So if this reaches the value, suppose see, this is the shape, this is the figure they've shown. If this is your safe region, if the value lies in this position, your structure will fail, but at this point and outside this region, your structure will fail. Within this region, your structure will be safe. All the values with this region, your structure will be safe. After this value, it will get fail. Okay, these are the conditions we have discussed. Now let's move to shear stress and maximum shear stress or shear difference theory, which is also known as Gassett's or Tresca's theory. Okay, I'll explain in this PPT. Let me. Okay. So as per this theory, it says that your maximum principal, your maximum shear stress, that means your tau value. Okay, your tau value should be, according to this theory, the failure or yielding of a component or material occurs when the working stress value reaches the limiting stress value in a material. So your tau value, shear stress means this tau, right? Your tau max should be, this tau max should be less than your sigma tau y. Sorry, that means your shear stress of the material should be less than the shear stress at yielding point. That means if I draw a, I'm annotating. Is it visible? Please let me know. I'm annotating with red color pen. It is visible.
Yes, ma'am.
Okay, thank you. Let me note once again. So as per this theory, the failure or yielding of a component occurs when the working stress value reaches the limiting stress value. Okay. So if I take a stress strain diagram again, this is my elastic region, yielding region, and this will be the break point. So this maximum, sigma max. Okay, as per this theory, your tau max, your shear stress, this maximum should be less than tau at yielding point. Okay, if I take this as yielding point, so your tau max should be your tau y. Okay, so usually for the 3D conditions, your if you go back to your engineering mechanics, let me add some students, they are in waiting. Okay, if you go back to your okay, first of all, it is applicable to your ductile material. Okay, for ductile material, what is the limiting strength is sigma y. Okay, was most important point, ductile material. And you can write the statement also, the failure or yielding of a component. Meeting is already unlocked. Meeting is already unlocked. Still it shows waiting. So first of all, this is for ductile material, which is for the ductile material, the limiting strength is your sigma y. So from engineering mechanics for 3D, if you take a 3D case, maximum shear stress is your sigma 1 minus sigma 2 by 2, or sigma 2 minus sigma 3 by 2, or sigma 3 minus sigma 1 by 2. Okay. So for 3D case, if you go back to your engineering mechanics, you will know that the shear stress tau max is the maximum of these three values for 3D case. Okay. But for 2D case, when sigma 3 will become 0, we'll have sigma 1 minus sigma 2 divided by 2, or sigma 3 will become 0, so we'll left with sigma 2 by 2 and sigma 1 by 2. So this values, we can get tau max equals, tau max is the maximum of these three values. So these three values should be less than or equal to your sigma y by 2. As per, if this theory says that the maximum shear stress should be less than your half of sigma y value. Okay, that means your shear stress, maximum shear stress of the material should be less than or equal to sigma y by 2. Okay, so this theory says that your tau max should be less than your shear stress on the material, your allowable stress, or permissible, you can say your permissible stress. This should be less than. What about others? Atul says that he is the only one who is not able to see. I'm dictating. I'm not dictating. I'm annotating in the screen with red color pen. Is this visible? What about others? Please respond to the chat box. He can see. So maybe it's clear. Okay. Okay. So for some maybe network issue, please check your connection. Okay, I'll continue. Okay, I'll continue. I cannot go back. I have to. Please check the recording. Okay. So your tau max value should be less than and equal to your sigma by 2. Okay. So you also you can say, so for let me. So for as per this theory, you will have these equations. As per this theory, you will have different combinations. Number one will be for 2D case, sigma 1 minus sigma 2 by 2 less than and equal to sigma by y by 2. So if I cancel 2, I'll left with sigma 1 minus sigma 2, which is less than and equal to sigma y. Okay, so this is the compression. If I can use this condition for tension, suppose sigma 1 is in tension and sigma 2 is in compression. I can change also, right? I can make this one as compression, and this one as compression. So I'll get another equation. Okay, again there will be four more conditions where I can take this one as tension and this one as compression, like that. Change sign convention. So I'll get four more conditions. Along with that, I'll get sigma 1 should be less than sigma y, or sigma 1 should be less than and equal to sigma y, This is the tension, this is the compression. Same with sigma 2, which is less than sigma y, or minus sigma 2, which is less than sigma y. So if I equate these equations in a single graph, then what I'll get? I'll get a figure like this. I'll get a figure like this. This is the value for minus sigma 2, so plus sigma 2. This is the value for plus. This is the value for plus sigma 2. This is for minus sigma 2. This is plus sigma 2, plus sigma 1. This is minus sigma 1. So I can join these points. Okay. Now for the rest of the equations, where I got sigma 1 minus sigma 2 less than equal to sigma y, and the rest of the combination, I can join these points. So basically I'll get this shape. Okay. I'll get this kind of shape for this theory, which says that your maximum shear stress should be your maximum shear stress, which can be found out sigma 1 minus sigma 2 by 2, or you can find sigma 1 by 2 should be less than equal to sigma y by 2. If I cancel 2, I'll get this value. So maximum shear stress. Okay, maximum shear stress means this one should be less than your sigma y for structure to be safe. Okay, so I can also write this one as tau permissible equals to sigma y by 2 FOS. So for design condition, we consider this factor of safety. Okay, so for design conditions, for design purpose, we take tau stress as this value sigma y. We take less value actually. We take less value of tau as this much. Whatever this value, it is always we took less value comparison to this value for the design purpose. And in the earlier story, in earlier stress, we used to take sigma 1 as less value of sigma y by FOS for design purpose. For design purpose. Okay, for design purpose, we need this factor of safety. Otherwise, our structure will fail. Okay. So now let me show you your PPT. See. So yielding will occur when the maximum shear stress reaches that which called yielding in a sample test. So this is the kind of figure, failure surface. So this is your safe region. After this position means some points after this region, this is called as safe region. Okay. If you get a value outside this region, then your structure will fail. Okay. Now next move to principal strain theory. Okay. We'll come to the rest the two theories. So we have discussed the two theories. Next come to principal strain theory. Okay. So according to this theory, yielding will occur when the maximum principal strain exceeds the strain at the tensile yield point in either tension or compression. So it says that if I draw a stress strain curve, this is my elastic limit. This is the breaking point. This is the stress. This is the strain. So as per this theory, the strain at this point, and this principal strain, what it says, it should be less than your strain at yielding point. Okay, the strain at the maximum strain The principal strain on the material should be less than the strain at the yielding point. The strain you get at the yielding, when the structure starts deforming, the strain you got should be less than the principal strain. Suppose you are getting here 50 Newton strain in a, sorry, strain doesn't have any unit. Suppose you are getting the strain value of 50 sigma 1. So, and the actual strain of the material is 70. So your structure is safe. Okay. Meeting is unlocked, dear. Meeting is already unlocked. Why is so- Let me try. Let me lock and unlock once again. Let me try. Okay. 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 So what I was discussed, yes. So strain of the material or the component should be less than the limiting strain. Okay, the strain at the extreme fiber should the strain in the material should be less than and equal to the limiting strength of the material. Okay, so you can also write this one as you know, stress by strain. Let me. You got some law, right? Remember, anyone remember that law? That stress by strain is nothing but Young's modulus. Okay, so instead of this strain, you can write stress by E. And this stress is nothing but sigma y by E. Okay. So this theory says that here the strain in the component material should be less than the strain at the limiting, the strain of the limiting, and it should be less than the limiting strain. Okay. And for the design purpose, you can write this one as sigma 1 should be less than equal to sigma y E into factor of safety. This is the no failure criteria. This is the no failure criteria. If this value increases this region, this value, so your the structure will fail. This is the no failure criteria, and this is for design purpose. We use factor of safety for design purpose. So this is the no failure criteria. This is for design purpose. Okay. So for strain, for a strain you have a formula. If you go back again, all these are interrelated. That's why I've asked in the first day itself, clear your engineering mechanics. So you can find a strain QD body like this, sigma 1 by E minus mu sigma 2 plus sigma 3. This is for 3D. Okay, this is for 3D. So finding the strain in a complex body where you have multiple stresses, you can use this equation in 3D. Okay, but in 2D you will have sigma 1 E minus mu sigma 2 by E. So this is for 2D. So this value should be less than sigma y by E. Okay. So as per this theory, the strain in the component, which you can find by sigma 1 by E minus mu minus mu into sigma 2 by E. So this value, so this value should be less than and equal to sigma y by E. So if you cancel out E here, you'll get an equation sigma 1 minus mu sigma 2 should be less than sigma y. Okay, same, this is one equation, this is equation number 1. You will get another equation, you can get more equations like this. If I taking this one as compression, so this can become minus sigma 1 plus mu sigma 2 should be less than and equal to sigma y. So this will become equation number 2. Again you can write, this is for sigma 1. I can take sigma 2 as a major principal axis minus mu sigma 1. Like this I'll get 4 equations, and if I solve this equation I'll get if I want to show in a coordinate system, so I'll get a shape of rhombus. If I represent this one as sigma 1 minus sigma 1 plus sigma 2 minus sigma 2. If I plot in this, if I plot those four equations in this coordinate system, so I'll get a rhombus shape. Okay. So earlier cases we got square, then we got another shape, then this, in this case it is in rhombus shape, and this theory is applicable for brittle material. Okay, so let let me show you the theory. See, these are the 1 by e sigma 1 minus mu sigma 2, these are the conditions given. Okay, now let's move to another theory, which is also known as strain energy theory. Okay, this is actually maximum strain energy theory, or you can say Haigh theory. Okay, so this theory is based on the assumption that the strains are recoverable up to the elastic limit. Okay, the strains we can recover till the elastic limit, and the energy absorbed by the material at failure up to this point is a single valued function independent of the stress system causing it. So basically, if I want to say in simple terms, so it states that the failure or yielding of a component or a material will take place when the strain energy per unit volume in a biaxial stress system reaches the stress energy per unit volume at yield point. That means the strain energy stored on a material, the strain energy stored in a material, the strain energy, suppose this is my material. Okay, the strain energy stored in this, everyone has some energy. Okay, so when I applied a load, the energy gets activated. So this energy, when it reaches the energy at its yield point, so this energy, this when this the energy in the stress, the energy in the this body, the actual energy in this body reaches the maximum energy, so it will be failed. To avoid failure due to this strain energy, the material must be operated below this yield stress. Okay, and according to this formula, you have you have a kind of mathematical expression which is like this. Let me write that sigma 1 square plus sigma 2 square minus 2 into sigma 1 into sigma 2 divided by m. M you can write, or Poisson's ratio you can write. 1 by m is Poisson's ratio, equals to sigma y by FOS whole square, or you can write this expression also. Okay, so this value, this part should be less than and equal to sigma y by 2. See, I have written FOS for the design purpose. Okay, so you can eliminate this one also. So sigma y square, so this value, as per this theory, this value, the strain energy, so this is the strain energy, this is the strain energy formula, this should be less than your sigma y square by 2e. Okay, this is for 3D cases. If you remove this 2e and 2e, you will get this expression. That means this expression for 3D, this value should be less than this value. Okay, and for 2D cases, this is the equation. So for this a structure to be safe for as per strain energy conditions, your this value sigma 1 sigma 1 square plus sigma 2 square minus 2 mu sigma 1 by minus 2 sigma 1 by sigma 2. See, I have represented here 1 by m, which is also can write as mu. Both are same, and you can say this as Poisson's ratio. So this should be less than and equal to sigma y square for 2D case. Okay. Again, this is applicable. This is applicable for your ductile material. And the we have discussed one shear stress theory, right? So that theory is safest theory among all these theories. Next we have shear strain energy or distortion energy, which is also known as von Mises theory, which is also known as maximum energy of distortion criteria. This is based on more complex view of the role of principal stress difference. So, in simple terms, if I want to say that, it states that the failure or yielding in a member or material occurs when the distortion energy value in a biaxial stress system reaches the maximum distortion energy at yield point. The energy, the total energy stored, the total strain energy, the total strain energy should be less than the strain energy at yielding point. Okay, so this is when the criteria is applied, its relation to the uniaxial tensile strength is this. So this is the criteria for uniaxial tensile strength for distortion energy. This is the criteria for distortion energy. Okay, so this is the formula for your equivalent strength. This is for segment. This is for 2D cases. So this is the expression for sigma E. In formulating this failure theory, they generally use Hooke's law. So this value sigma 1 minus sigma 2 whole square, this value should be less than your twice of sigma y square. It is same like the strain energy, and the shape of this safe region is this one. Obsolete you can say, or what will be the shape? Spheroidal, like sphere. Okay, the shape of the theory is this one. So the all the value should come within this. So value after this aid region, your structure will fill. So this is the safe region, and the shape of safe region is this one. And this is it gives very good results in ductile material. So this is for your ductile material. So I'll share this PDF file to you all. So there is a comparison. See, they have made a comparison of all the shapes. Okay, maximum principal strain theory, distortion energy, shear stress, and principal stress theory. And some questions given, which is which which came in gate. Okay, go through this PDF. Go through this PDF and let me know if you have any issues. Ma'am, it is not synchronized always. At what point it didn't synchronize? Okay. Write your roll numbers in the chat box. Please write your roll numbers in the chat box. Go through this PPT and let me know which part you didn't understand. Okay. I'll try to share my notes to you all if it is possible. I made some rough notes. I'll try to share. Okay. Before that, write your roll numbers. Please don't leave the class. Everyone wrote their roll number. Done with roll numbers. Roll number. Okay, please go through the PPT. I'll share the PPT. Go through the PPT and in the next class, Monday, we'll start new topic, shear force and bending moment. Okay. So this is about all about failures of theory. What is the first? Yeah, the important points in this module was what is the need of theories of failure. Okay, and the basic concept you need for this module is that you should know stress strain curve we have discussed earlier. Stress strain curve. Then from engineering mechanics you should know the Mohr circle, that how what is sigma 1 and sigma 2, that is your principal stress and major principal stress and minor principal stress. So if you know this two basic concepts, then you'll understand this theories very easily. And I tried. If you didn't understand, get back to me. Okay. And please go through this PPT plus your your sigma 1 and sigma 2, major principal stress and minor principal stress, and stress strain curve, more important, sigma y and sigma u for ductile and brittle material. Okay. Okay.